Hi, and welcome again to my physics online video lecture series. Today's video, we're going to be talking a bit about Ampere's law, again from an introductory algebra-based physics perspective, as best we can. So Ampere's law is basically a law that we can use to determine the magnetic field strength and actually direction as well, but predominantly we're interested here in strength of a magnetic field that is produced by moving charges. So in previous videos we've discussed how magnetic fields interact with moving charges. So recall from our previous discussion that magnetic fields apply a force on moving charges, but not on stationary charges and not on uncharged particles. So the magnetic fields are only applying force to charged particles which are moving. And that force was given by the cross product Q, that is the charge of your particle, V, the velocity, crossed with B, the magnetic field strength. And here again we find a sort of symmetry or parallel between these fields and the other fields that we know about. For example, we had the gravitational field, which we could summarize by saying Fg was equal to m times the g field strength. We also had the electric field, Fe was given by Q times E. But this right here, the gravitational field, it interacts with masses. It's also produced by masses. And the electric field, although it interacts with charges, the electric field is produced by charges. Now, if we turn to the magnetic field, it interacts with moving charges. It is also produced by moving charges. And this is largely in the form of current. So if we were looking at the magnetic field B, we could produce it from individual moving charges, but we generally consider the bulk effect of current. And so each one of these fields is produced by the same type of thing that they interact with. Now, Ampere's law is one way of essentially quantifying how much field is being produced by a given amount of moving charges, generally in the form of current. So Ampere's law, from an algebra-based perspective, says if I sum up around a closed loop the magnetic field B dotted with the sort of like little length elements around my closed loop, then what I get is some fundamental constant mu naught times the amount of current enclosed, which I'm going to abbreviate as I, E, and C. So this is Ampere's law. We need to give a definition for each of these sort of elements. Mu naught is what's called permeability. So this is permeability of free space. Just as we had permittivity of free space, epsilon naught for the electric field, and that was a fundamental constant, so now we have mu naught, the permeability of free space, and that is a fundamental constant. It has a value of 4 pi times 10 to the negative 7 Tesla meters per amp. Okay. Now, what about these other parameters? So let's say that I happen to have a magnetic field that locally maybe does this. Okay, so locally my magnetic field is just kind of uniform and pointing in some particular direction. Ampere's law says that if I have a closed loop in this field, let's say that my closed loop happens to look like this. If I take the dot product of the field with each of the length elements, so maybe this one right here is length 1. Let's say that we go around the loop this way, then we go this way. This would be length 2. This one right here would be length number 3. And then this side right here would be length number 4. Oops, should be drawn inside. Okay, well, we can see that in the case of delta L1, if I take the dot product between delta L1 and B, they're parallel. And so I should just get delta L1 times B. In the case of delta L2 and of delta L4, if I take the dot product with B, since they're both perpendicular to the magnetic field, this dot product in both cases will give me 0. And then last but not least, I have delta L3 dotted with field B. Well, delta L3 is pointing to the left and B is pointing to the right. So this product actually gives me a negative of delta L3 times B. So if I were to add up all of these around the closed loop, if I were to say, let's add up these 4 elements, I basically would need to do delta L sub I dotted with B, so over here, or B dotted with delta L sub I, either way. So this ends up being essentially delta L1B plus 0 plus 0 plus delta L3 times B, except for that, remember that this one was actually minus. And so if delta L3 and delta L1 and B, delta L1 and delta L3 have the same value and B is uniform, then this ends up being 0. So that in and of itself doesn't tell us very much about what's going on, but we could always pick for ourselves, for that same field, a different shape. So maybe I have one that's like this. So here's my field once again, and maybe this time I pick a shape that is more like a triangle, like this. And so now I have a delta L1, I have a delta L2, and I have a delta L3. And again, my shape needs to be closed. So it's a 2-dimensional shape, unlike Gauss's law where I need a 3-dimensional surface. And essentially, I would need to know what angles are being made between L2 and B and between L3 and B. So it's B dot L. So B dot L, basically I have an angle here, and I have an angle here that I'm using for those two. And so I'd have to take the dot product, I'd have to figure out what those angles are. Let's call this one maybe theta 3, this one theta 2. Then my closed loop of B dot delta L would now be essentially B L1 plus B L2 cosine theta 2 plus B L3 cosine theta 3. And so if I know what the angle is, I can put those cosines in. These may end up being negative values, they may be positive values, whatever. I'll end up getting some value for my magnetic field. Another possibility, of course, is that I could also maybe pick a simple geometry like this that is partially in the field and partially out of it. And so this one, if this is, call it delta L capital 1, delta L capital 2, or Roman numeral 2, 3, and 4. This one, I'm going to end up with sum of B dot delta L is just equal to B delta L1. Everything else is either perpendicular and thus 0 or just outside of the magnetic field. Okay, so that defines that term. What about the enclosed charge part of it? Well, if I have let's say a loop that is triangular like this, or square or circular or what have you, then that loop has with it a cross section. I'm going to shade the cross section in this kind of yellowish color. And through that cross section, there could be some amount of current. So for example, if I have a wire that is sticking up out of the page at me like this, and I've got current flowing through the wire out of page or out of screen, then this entire current passes through this enclosed area, and so I enclosed would equal I. Now let's imagine that I have several such of these wires, and each one of them carries a current I. But some of them end up inside of this area and some of them don't. So each one of these has I, this one has I, this one has I, this one has I, and I. Well, now two of these are inside the enclosed triangle, and so my enclosed current would be 2I. Let's consider one more example. All right, in this example, I have current coming out of the screen if it's a circle with a dot, and current going into the screen if it's a circle with an X. So again, I look at this one, I have 2I coming out and I have 1I going in, so my total enclosed would just be 1I. All right, so that is kind of how those parameters are defined. Now, how might we use this law? Well, let's consider a long straight wire. We'll give it both a side view and a top view. Now, this long straight wire, if it's carrying current, is going to produce a magnetic field. I can map out the direction of the magnetic field by taking a compass and placing it around the wire and seeing what direction the needle deflects in. So maybe I do that and I find that one possible magnetic field line is this. So if I trace around this, I get deflections from the compass needle to kind of make this counterclockwise circle. In this plane, maybe that circle looks like this. So it's again counterclockwise. It's centered, or it's supposed to be centered, on the circle. So let's move this guy over just a hair, like so. And then I want to apply the Ampere's law. Well, my B delta L basically just ends up being dotted with little L elements, delta L, around this circle. That basically means that I'm going to end up getting this. B delta L round this circle will just be B times the total length or circumference of the circle. But that's just 2 times pi times whatever the radius of the circle is. So then I set it equal to mu naught I enclosed. But that's just the current carried by the wire. This lets me solve for the magnetic field strength. So that is it.